You call that a knife? Well, I see we've all played Knifey Spoony before. So I thought this week we'd tackle a few things at once. I've always wanted to make a knife at least once, and I think after all these years I might as well give it a go. But at the same time, I also want to do a video about heat treating steel. For a topic that pretty much boils down to being heat metal up to red and then cool it down quickly, it can be a lot more complex once you dive into the theory behind it, and I think there is a fair amount of misunderstanding on the topic. And you know, I can understand that. For instance, let's take these two pieces of steel. They're both tool steel and they look almost identical, but if you were to heat them up and quench them in oil, one of them would be relatively unchanged, whilst the other one would be in the 60s Rockwell C hardness, which is very hard for a metal. But before we talk about alloy and tool steel, I want to go over plain carbon steel first. It's the most basic type of steel to heat treat, and it's probably the most straightforward to understand. And by carbon steel, we're talking about steel where the composition is iron and carbon for the most part. And as a percentage, carbon is going to make up about 0.05 to 2% of the metal. Once you go above that, you start to get cast iron, and that is a very different metal in terms of its physical properties and heat treating. Now generally you will get some phosphor or silicon or sulfur mixed in, but we won't worry about that a whole lot here. What we're really focusing on is the carbon, because when it comes to steel, and this includes alloy steel, the amount of carbon really does make the difference when it comes to determining the physical properties. And that being how much carbon there actually is and how it's arranged in the internal microstructure of the steel. Case in point, this is mild or low carbon steel, and you see me use this stuff all the time. This stuff has about 0.2% carbon, and it's a really good steel to work with, and it's a relatively strong metal. But if we took this same piece of steel and raised the carbon content so it was closer to about 1%, it might be twice as strong, and that's nothing to do with heat treating, that is just the effect of what a small amount of carbon can do to steel. Speaking of heat treating though, low carbon steel, well, stuff lower than about 0.3%-ish, won't readily respond to quench hardening. I mean, you can try it, but not much is going to happen, or at least not enough to make a knife. You can definitely affect some of the properties by quenching it, but you're not going to be making a knife from it. However, there are reasons why you would want to heat treat mild steel. For instance, this is a piece of cold rolled plate which I use all the time. It's also mild steel, but it's also going to be a lot stronger and harder than a piece of steel that's been hot rolled. You can generally tell a piece that's been hot rolled or cold rolled because hot rolled steel will have that flaky mill scale. Now the reason why cold rolled is going to be harder and stronger has nothing to do with the carbon, but it's all down to the cold forming process. When it's actually rolled in the steel mill, it's been crushed at a low temperature, and as a result, the internal microstructure has been crushed and deformed. If you've ever bent a piece of metal, you know that it tends to get harder to bend the further you bend it. And that's pretty much the same thing here. You're bending and distorting the microstructure, and the more you bend it, the harder it becomes. The big problem with this though is that it leaves the steel with a lot of built-in stresses which can cause the part to warp if you heat it up or weld it or machine it. And unfortunately, the warping might not be present until you take it out of the vise or the chuck. As an example, I'm going to be machining down a piece of cold rolled plate, and I'm going to be taking all of the material away from one side only. And in doing so, that should leave the internal stresses sort of unbalanced, so to speak. Now I know that the mill should be adequately trammed, so the piece should be perfectly flat whilst it's still in the vise, but once I take it out of the vise, you can see that it's no longer flat. The stress in the steel has warped it. Now, as you can see here, it's not a whole lot. I could only fit, say, a 10 micron shim underneath it, but at the end of the day, that's still 10 microns too much, and depending on the tolerances of the part and the drawing, that could easily account to a scrapped part. Now, if we further heat or unevenly heat it, we can cause it to warp even further. It probably doesn't look like a whole lot more on camera, but I can now fit a 15 micron shim underneath it. Now, generally speaking, this shouldn't happen on steel that's been hot rolled, since the forming process takes place when the steel is red hot, that's above the recrystallization temperature, and as it slowly cools, it should leave it with a relatively stress-free, normalized microstructure. However, hot rolled steel isn't dimensionally accurate because it tends to shrink as it cools, so what a lot of people do is they'll take their cold rolled steel, which is dimensionally accurate, and then they'll put it in the furnace at about 500 to 600 degrees for a few hours, and that should relieve the stress. Doing that is effectively a reset button for the microstructure, and the resulting material shouldn't be stressed. You can also buy steel that's already been normalized in a furnace, although you are going to pay extra for that. Anyway, let's get back to the project at hand, and that's going to be to make a knife. I suppose if I'm going to be making a knife, I might as well make something that is different to one that I already own. So what I'm going to make here is a Japanese style single beveled knife. I've always wanted one, so I think this is the perfect project to get one, although the big downside to them is they can be a lot more difficult to use and sharpen. Now, when most knife makers start off these projects, they'll generally start with a blank of 1055 or 1080 or 1095, effectively high carbon steel. However, for this project, I'm starting off with the cheapest, crappiest steel that I could find. This is a piece of 25x6 mild steel flat bar from Bunnings, and it is low carbon and it is not suited for knives. I think knife makers would call it low quality steel, and it might be, but with a small amount of metallurgy, we can very easily make a perfectly usable knife out of it. Carbon steel is just metallurgy, so it should be just fine. With that said though, this is purely for demonstration. If you were going to make a knife, just start out with a piece of high carbon steel flat bar and go from there. Anyway, the belt grinder, I'm going to do my best to grind the blank down to the shape that I'm going for. I'll then add a scribed line as my guide, and I'll slowly work my way up to the scribed line to form the bevel. It's also worth pointing out that since I'm right-handed, the bevel on this type of knife will go on the right side. From what I understand, if I was a lefty, that would be the opposite. The single beveled knives also tend to have a hollow grind on the backside, and I gave it a shot at adding it, but the results were kind of mixed. I can now take it over to the workbench and try to get some of those deep scratches out of it. Alright, it looks pretty good so far. With the knife blade now roughly done, we now need to get started on our first heat treatment stage, and that's going to be to get more carbon into the steel. Like I said before, this is mild steel, so there's not enough carbon to get it hard enough, so we need to add more carbon into the steel. There's quite a few methods which we can do to achieve this, but I think the most basic in a home workshop is to pack harden the part and case harden it. I have a dedicated video on the subject, but in short, the piece of steel is going to be placed in a steel packing box. It's effectively a piece of tube with the bottom welded up. I'll place the knife into the box and then I'll pack it in with a mixture of crushed up charcoal and sodium carbonate. The charcoal is going to be our main source of carbon, although the sodium carbonate does help in the early stages. Some people do add barium carbonate, and there are a few other things which you can add, but I think sodium carbonate is a good addition because it's very cheap and you can buy it as washing powder. I can then seal the top off with a heat-proof plaster or cement, and then I can get it in the furnace. Now this process will take about 30 minutes to start working, since the heat needs to travel all the way through and heat the steel to 720 degrees Celsius. At that point, it can start to absorb carbon. And it's going to be getting that carbon from the charcoal and the sodium carbonate, but it's not directly diffusing it. What's actually happening is, at these high temperatures with little oxygen, they both start to break down to produce carbon monoxide gas. The carbon atom will then split off and diffuse into the steel, and the spare oxygen will bind to create carbon dioxide. Now the carbon builds up on the outside of the steel and it works its way into the centre at a rate of about 0.01 to 0.02 millimeters per hour. It's a very slow process, and I've seen videos where people will spend days maintaining furnaces to get the carbon to diffuse deeply into a piece of steel. And effectively what we're doing here is encasing the part in a high carbon steel case, hence why this is known as case hardening. Now this can be really beneficial for some parts because you're able to retain the tough low carbon steel core, but also increase the hardness of the outside, and that's why this can be used to make gears. The outside, once you quench it, will have increased wear resistance, but the tough core should resist any shattering or fracturing. It's also worth noting that if we started to fold the steel, we could start to distribute the carbon throughout the steel more evenly. Obviously, it's not the only reason why you would fold steel, but it is definitely one of them. Now after a few hours of hardening, I'm going to leave it in the furnace to cool overnight. Now the fact that I've left it in the furnace to cool overnight means that the steel has been allowed to anneal, and that will have left the new high carbon steel layer in its softer state with minimal internal stress. Now the exact reasons for this are not hugely important when it comes to home heat treatment, but in short, the slow cooling has allowed the carbon atoms to bind with some of the iron atoms to form iron carbide or cementite. And this is only true for a fraction of the steel because most of it is still left as pure iron. Now the small amount of iron carbide or cementite has a hardness of 72 Rockwell C hardness, whilst the ferrite or pure iron has a hardness closer to 0. The resulting hardness is going to be anywhere from 0 to 20 Rockwell C hardness, and it's going to be dependent on the amount of carbon. More carbon results in more iron carbide forming, and as a result, the overall hardness will increase. Now that obviously is a bit of an oversimplification, but the important thing is we now have a case of high carbon steel which we can now harden. And we need it to be in the 50s or 60s Rockwell C hardness to use it effectively as a knife. So what we need to do is we need to heat it back up to red and then cool it down to reharden it. We need to get it up to red so we can start to reshape and reform the internal crystal lattice. Now it's worth pointing out that the overall carbon content is going to determine the maximum hardness that we can get, although it is not perfectly linear. 1045 won't get as hard as say 1095, however the difference is not that big. I've gotten close to 60 Rockwell C hardness with 1045, whereas 1095 only pushes about 68 Rockwell C hardness. With that said though, I generally don't ever know the final carbon content of the case harden, but I can very easily get 65 Rockwell C hardness. So I'll coat the knife in a flux, and that should protect it from oxidizing at high temperatures inside the furnace, and then I'll get it in the furnace and get it red hot. Like I said before, we're effectively resetting the internal microstructure of the steel, so how we go about cooling it will determine the microstructure and the hardness. Now, even though we should be able to get a high degree of hardness from this steel, plain carbon steel has a lousy hardenability, which among many things means we need to cool it down very quickly to achieve that maximum hardness. For plain carbon steel, for example, we have about 1 second to get it from red hot down to about 150 degrees Celsius to get it hard. Okay, once again, it's not that simple, especially if you go off the TTT diagram, which dictates the grain structure that can be achieved through time and temperature, but for a home workshop setup, we can effectively ignore that for the moment. The real question is, well, what do we quench it in? Do we quench it in water or oil? And I've had people comment that water quenching is somehow bad for steel, and for the most part, I understand the sentiment, but I disagree. Water, and by extension a 10% salt brine solution, is going to offer you the fastest quench for steel, and it's going to give you the maximum hardness, at least for plain carbon steel. And for me, it is my preferred method for quenching parts, not because it gives you the best results, but mostly because it is the easiest method to set up and then dispose of. You know, for some of the parts that I'm doing, I need easily 20 litres of water, and it is a lot easier to set up 20 litres of water in a tub than it is to set up and then clean up and dispose of 20 litres of oil. The big downside to water though is that because the part cools down so quickly, there is a big risk of the part cracking as the part cools down, contracts and becomes more brittle. And especially once parts become complex with thin walls and internal cavities, then you can have a lot of issues. As the part cools down, you also want it to cool down evenly, and if it's unevenly cooled, it can cause it to warp. And when you quench in water, there is a huge risk that if the part doesn't cool down evenly, the part is going to warp and distort. And if that already wasn't bad enough, the water will then turn to steam and it will coat and stick to the part and further cause it to cool down unevenly. Now, a 10% saltwater brine can help reduce this, but there's only so much that salt water can do, and you end up using a fair amount of salt to achieve it. On the other hand though, oil cools at about 1/3 the rate of water, so the risk of distortion and cracking is far less. But generally with carbon steel, it will tend to result in a part that isn't as hard, although it seems to be very dependent on the mass of the part that I'm quenching. Smaller parts tend to come out closer to 60-65 Rockwell C hardness, which is very close to water, but as the part gets bigger, it tends to drop into the 50s. I've also played around with using hot oil or small volumes of oil to reduce the rate of cooling to help reduce the potential for warping, and that seems to work well, but it does leave the hardness in the high 40s to low 50s Rockwell C hardness. Now, there are special quenching oils with specified cooling rates that they do sell, but for home shop use, I've always used vegetable oil and they work just fine. Most oils tend to cool at a very similar rate, and for home workshop use, you really aren't going to notice the difference. The only big downside to using oil is the cleanup and the residue that's left on the part. It's polymerized oil, which is very similar to seasoning a carbon steel wok, but it can be a nightmare to remove. Sodium hydroxide tends to help break it down, and then steel wool then helps remove the rest. Now the final hardness we're left with is just shy of 65 Rockwell C hardness. There's quite a few hardness testing tools which you can buy, and they can get you a very accurate reading on how hard something is, but I think for a home workshop, using these hardness testing files should be good enough. As per the files, the 60 Rockwell C hardness file doesn't bite, but the 65 is only just starting to, so the hardness is just below 65 Rockwell C. Now the reason why quenching is able to make it so hard is all down to that rapid cooling. The carbon is not able to diffuse out and form cementite, but it instead forms something called martensite, and that makes the steel incredibly hard. However, we can't leave it like this because rapid cooling has left the steel incredibly stressed and brittle. It's effectively lost all of its toughness and it's very easy to shatter. Although it's worth pointing out that heat treating steel won't change its flexibility, that always stays the same. Now the next step is to reduce that brittleness and get some of that toughness back, and that's going to be in the temper step. Sometimes I do skip tempering with case hardened parts, but since the blade has probably hardened all the way through, I am going to have to temper it. In fact, just to show you how bad it was, I tried to sharpen it on a whetstone and the edge kept chipping. Now thankfully, tempering carbon steel is a pretty straightforward process. You heat it to a desired temperature and you soak it there, and the hardness will drop, but the toughness will increase. Now the hardness that you get when tempering is pretty much proportional to the temperature that you temper at, although it's not linear, and there are graphs for each type of steel and the final hardness that you will get. Now some people heat the steel with a blowtorch and use the oxide colour as a sort of guide for the steel's temperature. The oxide colour changes depending on the steel's temperature, but I prefer to simply pop it in the oven and leave it for an hour. The amount of toughness that you get from steel, however, is going to be all over the place, and it's going to change based on the alloy. As you can see in the graph, it drops and rises several times, and you'll want to make sure that the temperature which you temper at is pretty much spot on. For example, with W1 steel, the difference between 180 degrees and 200 degrees for the temperature can represent a huge change and drop in toughness, so make sure that your oven is accurate. Thankfully though, once it has been tempered through, it is much more receptive to being sharpened without shattering. Unfortunately, it does look like the blade has warped a little bit during heat treatment. Now, since the core is unhardened and still quite ductile, I could probably bend it back into shape, but I don't want to risk the blade cracking. It's probably hardened all the way through, and if I tried to bend it too far, it would probably crack on me. It has been tempered, but it is still quite hard, so I don't want to risk it. In theory, if I really wanted to, I could heat it up and anneal it so it becomes fully ductile, but then I'd have to repeat all the steps again, and you know what, I'd probably end up warping it again anyway. Now I didn't mention it before, but heat treating is really a last resort for me, and I only do it if I absolutely need the part to be incredibly hard, and that's because of the risk of the part warping or cracking. Cracked parts are especially annoying because that is pretty much game over and I have to restart from the very beginning. Warped parts aren't as bad, but they will need to be ground to spec again, and that's why it's always worth making parts that need to be heat treated a little bit larger than they need to be, because anytime you have to grind it back, that is more material that needs to be removed. And unfortunately, since I don't have a proper surface grinder or grinding setup, grinding parts back into spec can be very difficult. Now in theory, carbide can cut hardened steel, but it does a very poor job and is generally never flat enough to be a good result. There are other materials that can cut hardened steel, but they are either too expensive or they won't last long enough for me to use. call that a knife? Well, you know what? I certainly do. And you know what? It is certainly sharp enough, and for a first attempt, I'm really happy with it. And for being made from garbage steel, I think it's probably just as good as any carbon steel knife. Now, on a final note, believe it or not, there is still a lot of information that I wasn't able to squeeze into this video. I had to simplify a few things on carbon steel, and we completely skipped over looking at TTT diagrams. Plus, I left out alloy steel completely. So I think we'll have to tackle that another time, but I think for a basic home workshop heat treating video, this should be perfectly adequate. And if anyone's wondering how the knife actually performs in the kitchen, well, it works pretty well. I'm as much of a chef as I am a machinist, and I gotta say, the knife works really well. I'm pretty sure one of the tests for determining how sharp a knife is to cut through some onions, and I gotta say, it cuts through those onions really well. No joke, I have a spare set of safety glasses dedicated for cutting through onions, and this time, the cut was so clean that I didn't need them. All in all, I gotta say, that's a pretty good result. And that's about it for now, guys. I hope you enjoyed this one. Thank you very much for watching. I'll see you next week.